Soumitra from IIT Bombay, who's going to tell us about recovery of a sparse integer solution to an undetermined system of linear equations.
Okay, hi, good morning. I am Soumitra, and this is joint work with T.S. Jairam of IBM Almaden, who is currently visiting IBM in Research India. I work with him, and also Vijay Arya of IBM India. Okay, before going to the problem, let us motivate with a application. This application comes from smart grid, where energy is distributed from the distribution side to the households using 3 different phases. Each of these households is connected to one of these phases. So when the connections are made to this household, the distributor knows that this house is connected to this particular phase. But after a certain number of times repair, because of repair or some other reasons, this phase assignment gets changed. But the distributor doesn't know about that. But for the distributor, the phase assignments information should be there with him, because this helps in reducing the imbalances. And if there is an imbalance in the phase loads, then there is a huge loss. So to make the phase imbalance loss very low, he has to know exactly which house is connected to what phase. So in this problem, we are going to solve this phase assignment problem. Okay, so simple approach would be something like you shut down one particular phase and see who are the households who are complaining, and that is very naive, but that is disruptive. You cannot. There might be some service contract agreement, and you have to give a lot of money back. So other could be sending a crew to each and every house and see which house is connected to what particular phase. But again, this is very expensive. So it seems that there are lots of data with the distributor regarding what is happening in the electrical distributed network. So these smart meters, after every certain time interval, these meters send how much energy was consumed by that particular household. So these data are coming to the distributor, and also from the distributor transformer side, the distributor knows for this particular phase this much energy was spent for this particular time interval. So we have these 2 sets of data, and using these 2 sets of data, can we come up with some mathematical algorithms to find out the phase? Okay, and there might be some errors in the measurements. Maybe some of the houses was switched off or something like that. There was no data, or there may be some synchronization error because the time interval that at the transformer side, the measurement and the household measurement, there might be some synchronization error, and also there might be some transmission loss because the power is coming through the cable. But for our work, we assuming these errors to be 0. Okay, so problem formulation. So let us formulate this problem for a particular phase. So input to this problem, there are there is one matrix. The ijth element of the matrix gives the energy consumed by a particular house J in the ith time interval, and Bi the transformer reading at the ith interval. And the output of this problem, we have to come up with a binary vector X. So Xj denotes whether a particular house J is connected to the phase P. Subject to the constraint that the energy conservation law is satisfied, this term AIX denotes the total amount of energy consumed by all the households, and Bi corresponds to the energy sent from the transformer side. So we equate these two quantities, and we get this constant. Here also I mentioned that we ignore the losses. So if we solve this problem individually for each phase, and we can we can guarantee that these solutions are exact, then after getting back the solution for each of these phases, if we simply combine those solutions, then we should get the overall solution. So observation. So to get the exact assignments, we have to come up with some solver to this is Ax equal to B, this set of linear equations, such that the solver has only one solution. There is only unique solution, so that when the solver solves that, whatever results it gets back, that you can assume that since that is the unique solution, that is the phase assignment. So if there is only one measurement, then this problem becomes a subset sum problem, which is classic NP-hard problem. On the other hand, if there are enough variability in the measurements and we have enough number of measurements, then if the rank, if the whole system is full rank, then you know that there is a unique solution, and simply solving that linear equations will get the solution. So, but the question we ask, that is there a possibility that using lesser number of measurements, can we still achieve the uniqueness, so that the solver takes lesser number of measurements and we get the solution? So this is the research problem we wanted to tackle, and for this talk I will focus on that case when it is known that the number of houses connected to a particular phase is some small quantity k. So we want to devise some algorithm so that even in this case it takes if the sparsity is small, can the algorithm find out the solutions using lesser number of measurements. So for this, our contribution is that we take this LP based recovery algorithm, which minimizes the sum of all xi's with respect to this constant, and then we give a necessary and sufficient condition for getting the exact recovery, and for a random matrix with random matrix A with the property that the columns are interchangeable, we try to find out the probability of this the condition for this exact recovery is satisfied, and we show that finding the probability is related to a well-known problem in geometry, namely the K-set problem, and as far as our knowledge goes, this connection is new in computer science. And using the empirical data, we conjecture that for sparse solution, the recovery will be something, the number of measurements required for exact recovery will be something like n into hn by k, where h is the binary entropy function. So the outline of the talk will be, I briefly mention the previous work, and then I go through these two theoretical results, getting the condition and the probability of getting the condition satisfied, and then I mention the simulation result. One of the previous work is by Mangasarian and Ray. What they did, they took a modified, the transform version of the problem, where they used signals, binary signals of values plus and minus 1, basically map 0 to minus 1 and 1 to plus 1. And for this system, they gave conditions for exact recovery, and also for random matrices, they showed that there is some kind of phase transition behavior of this recovery LP. As n is large, it seems that when number of measurements is less than n by 2, then it cannot recover at all. But if the number of measurements is greater than n by 2, then this LP recovers exactly. But the problem is that they didn't consider the sparsity of the unknown solution. The work which considers sparsity of the unknown solution is by Donovan and Tanner, but they considered the sparse solutions to be identical to a solution in a k-dimensional space of that polytope. So using their notion, a k-sparse solution or a point in k-dimensional space has k entries with values in between 0 and 1, excluding 0 and 1, and n minus k entries with values fixed either 0 and 1. But with this notion of the sparsity, a binary solution is always 0 sparse, because there is no value in between 0 and 1. So we cannot use this S-counting method. To use their notion of sparsity, to use their approach for our notion of sparsity, we have to relax, we have to use a weaker constant corridor. But in this case, since the corridor is constant, we are losing something. So both the LPs they use is are lacking something or other. So we concentrated on the thing that the sparsity should be according to the our definition, that number of ones should be k and number of 0 n minus k, and it should be just that LP that we consider. So now we go to the uniqueness condition for this LP to have a unique solution at a particular point. Let a solution to this LP be x, and you divide the indices of x into two parts, where the set of indices where the x takes value 0 and another set where it takes 1, and you see the corresponding columns of the matrix. So I have given an example. Now for the columns, and we represent each of these columns as a point in R to the power m space. So in this case, all the columns for which x has value 0 I am representing by red, and all the columns for which x takes value 1 by green. So the theorem that we gave in the paper is that x is a unique solution if we consider two convex cells. One convex cell is of the points of red points including the origin, and another is the convex cell of the green points. If these two convex cells has a common point, then there cannot be any unique solution. So for the uniqueness to happen, these two convex cells should be mutually exclusive. There should not be any common point. So for this problem, if we take a convex cell, we can see that these two are disjoint, and in this case it will be this particular solution x bar is unique. You take another example where the positions where x is 1 is changed, and in that case these two convex cells are not disjoint, so it will not be unique. So I am not mentioning the proof of this theorem. It is in the paper, and it is a simple application of a very old result by Mangaswaran himself, where he gave the conditions for a general LP, the uniqueness conditions for of a point of a solution of a generic LP. Now I go to the you can see that there is some notion of points and the convex cell. So this K-set problem is very much related to that. A K-set of a set of points in equilibrium space is a subset of size k, so that those points can be separated from the rest of the points using a hyperplane. So it's not this I took from Wikipedia, where I have given 6 points and 2 subsets which can be separated from the others. Okay, now I show the relationship between the probability of getting the exact solution and the K-set problem. So by P M and K, we represent the probability that exactly requires K per solution for a random n by n. And suppose that A is drawn from a distribution where changing the columns doesn't matter. In that particular case, P M and K is equal to expected number of K sets divided by NCK. So you generate the random matrix A, you see the columns where and see the points in the R to the power n, and see how many of them are, what is the expected number of K sets for those points divided by NCK, that will give the probability. This comes from this. We get an indicator random variable for each of these possible K sets, and if that K set is, if that subset of size K is actually a K set, you set the random variable 1, otherwise it is 0. Then you can see that since the columns are exchangeable, so the probability that a particular subset will be actually K set is, it doesn't matter which subset you are picking. So that in that case, all of them will be equal to PMNK, and this gives that PMNK is equal to expected number of cases divided by. So this case problem has been studied in combinatorial optimization problems and all, but there the focus was to find out what is the maximum number of cases possible for a particular set of points, and but there is only one work where they have considered for random set of points, but the random set of the result they give is some kind of upper one, but for our probability calculation we need something like some lower bound, so we cannot use that example. Now I go to the simulation. So we simulated these 3 different recovery algorithms, and we generated random instances and 200 random instances for each of these data points, and we plot the success rate, how many of the 200 was actually successful in recovering the solution exactly. So first I give the comparison between the Donald's LP. So here we plot on the x-axis data to m by n, the number of measurements as a fraction of total number of variables, and on the y-axis the sparsity k as a factor of number of measurements, and in the z-axis the success rate. Now if we see the level sets for the success rate, particular success rate, we see some curve like this. If you take another success rate, we get another curve, and this success, as we increase the success rate, we see a band. And Dono and Tanner mentioned that these bands become very narrow as n becomes large. So this divides the region into 2 parts, and it shows transition. So we did similar experiment for our LP, and we saw that the curve actually goes up for earlier. So the curve, the region below this curve is where the probability, the success rate is high, success is 1. So we can see that the region for success rate only for our LP is more. So then we compared with the Mangasarian's LP, and here we only show the level set for 0.5, and we see that and here we plot against sparsity versus the number of measurements, and we see that it doesn't vary on sparsity, and we plotted the variations of our LP, and we see that this roughly matches this bounded entropy function, and I have also shown that the standard log bound in competency that in log n by k, and we have shown that we use an LP which does better than both Mangasarians and autonomous. And I also call conjecture the closed form, but we need to prove that conjecture, and also we need to consider the measurements. Thanks, and I sincerely acknowledge that support that Mathus has provided for my talk. I have kept a copy of this paper and archive, and if you want to consult, you can. Any
Questions?
So if I'm trying to understand, when you talk about success rates in your original problem, I'm from the Bay Area, so I had my smart meter put in recently. So did you actually measure this against the reality? Did you use a real data set?
No, we generated because one thing I forgot to mention is that the random matrix A is from standard normal distribution, so that can have something like value negative. The standard normal with mean 0, so it can have some negative, but in negative values in smart meter doesn't make sense. So we also did some experiments on keeping something like normal distribution but non-negative mean. So for that we also seen the curve similar. So I have mentioned in the paper, but the lack of time mentioned.
Other questions? So I have a question regarding one of the last curves that you've shown. before the one before that. Yeah, that's right. So in the case of your curves, it seems that there is a regime where sparsity does matter, and then a second regime where let's see, you can take rho going to 1, right? So maybe there are two different regimes of behavior of the algorithm. I mean, do you have any comments on that?
We have not done any theoretical analysis while we are getting the curve. The Donovan, they have given theoretical analysis of how you can get this curve, because they use that phase counting methods, and through that they have proved that, but we have not done any theoretical. But our basic understanding is that if the sparsity so k by m is equal to 1, that means what? That number of measurements is equal to the number of sparse vector, right? So in that case, you are expected to get the exact recovery.
Sure. Then basically what you're saying is that if your number of measurements is roughly half
if number of measurements is half, means you have enough measurements, and in that case, sparsity is denominated. Yeah.
Other questions? Okay. Let's thank the speaker again.